Hello everyone. Week number 4. It's week number 4. Only 2 weeks left for my teaching, which is very good. I mean, from my perspective. Plus, next week we're going to have quite a short week because we not only will have a Good Friday, which steals 1 lecture from us, we also have test on Thursday, which steals another lecture from us. Yes. So if I can please, if I can possibly have your attention right now. If I can possibly have your attention right now. Yeah, thank you. I plan to discuss today with the subject of Lagrange multipliers. This is the last technique which in relation to min-max problems. So typically what happens with the Lagrange multipliers, it is applicable when you're trying to find a max or mean of a function subject to a constraint. Let me just double check something. Yeah. When you try to find mean or max of a function subject to a constraint, it is very often a good case to use Lagrange multipliers method. It's a very good method, very effective, but it's a new method to you. So you will struggle a little bit before you get the grasp, because you grasp the ideas of the method. Now, there are a few problems on this set of slides which demonstrate the method, and there are a few problems here. But before we go, I'd like to discuss with you, the first problem here, for instance. If you look at the first problem, look at this, what happens. You need to maximize or minimize this linear function, double x plus 3y, but you don't care about the max or min of this function across some domain or locally. Instead, you only care about max or min of this function subject to the constraint of this type. So you only care about max or min of this function when you consider this function only on the circumference of a circle's radius 2 centered at the origin. It's a typical case where Lagrange multipliers are very effective. But before we go on, I'll show you that this particular problem, problem A, can be done with the methods we discussed with you on this week, earlier methods. Like, remember when we did this triangle problem, min-max over the triangle? When we did the boundary, we parameterized the boundary 3 different ways, and we restricted our function on that boundary and studied function of 1 variable. You can do the same trick from the part A here. Easy. And I think it's worth knowing that trick. Look at this. I'll show you this trick. It's on a different set of slides. Here, the same problem, find the extreme values of function x double x plus 3y subject to the constraint x squared plus y squared equal 4. We can proceed the way we proceed with the triangle problem. We can parameterize the boundary. In this problem, it's a perfect case to do that because circle has a very beautiful, symmetric, and nice parameterization. Here it is. If I take the parameterization for my circle, canonical way to parameterize a circle, and if I restrict my function onto this parameterization, it will be the case which will help us to solve this problem. Look at this. If I now take my gt function, which is my f on this specific parameterization, it will be my function on the boundary. Alone, nothing else. So here's my function. Double x plus 3y, but now cos t sine t, over this interval, and we have to minimize and maximize this function. It's a first-year problem. Minimize the function over the domain. That's something we experienced 3 times with you when we did the triangle boundary, because on triangle boundary we use 3 different parameterizations. It is even better here because we use this beautiful parameterization for the circle. For the boundaries of triangle, it's boring because it's a line parameterization. Here, it's shiny. Okay, so how do we do it in the first year? We compute the derivative. Here it is. Derivative of my function. We equate that derivative to 0. We come up with a solution. These are the stationary points. So this solution, it's a trigonometric equation. You can just take, say, 6, and then it's a 4 sine on the other side, divide everything by cos. You will end up with the equation tangent t equal 3 on 2, which we know how to solve. Within this interval, this has 2 solutions. It's the first solution. That's the second solution. These are it's a opposed solutions. They sit on the different ends of the diameter. These two solutions, here they are. This is a T1 point, or this is T1 angle, I should say. This is a T2 angle, plus half of the revolution. Two of these angles, they provide, if they give you a solution to this equation, these are the 2 points you have to study. So before you proceed, you have to find the cos and sine at these values. It's another elementary task, which you know even from the school, how to find the other trigonometric functions if you know the value of one of the trigonometric function. In this case, we know the value of tangent, 3 and 2, how to come up with the values of the sine and cos, which is associated with that. It's an elementary task. It's not a unique solution. There will be 2 values, one of them, with 2 values, of course, one of them here, one of them here. So for the T1, you got sine and cos like this. I'm skipping some trigonometric evaluations because it's a part of the elementary school. High, but still elementary school, how to do that. For second value, these are the values of sine and cos. And we're done. Now I have to compare the values of my g in these 2 points, which if you reflect back in terms of f, you have to compare. So here's my comparison, g of t1, which is f of double cos t1 free sine t1, and that is the value at this point of my function, and that's the value of my function at the second point. This is the max, this is the mean. Would you agree with that? Basing on your first year experience, would you agree with this? There's something hinting probably you shouldn't, right? Yes, no? No. Why no? So why no? Maybe yes? Well, the first year method, on the top of checking the values of your function everywhere the derivative is 0, it insists as well on checking the value of the function at the endpoints of the interval, which I didn't do. So the answer is no. It's not a complete solution. My interval, my g function of one variable, first year stuff, nothing serious. We found those 2 points where derivative is 0, but we didn't check negative pi. Well, in this case, it's actually 1 point. It's not 2 points. Because even though in terms of t it's 2 points, back in the parameterization language, it's 1 point here, -1, right? Under this parameterization, both negative pi and pi, they all end up in the same point, this one, -1, 0. So I still need to check the value of my g at negative pi and pi, which is f of -1, 0. I still need to check this line. I mean, I need to make this check before my solution will be complete. Well, it's an easy check, isn't it? F -1, 1, -1, 0, I'm sorry. My function is, here's the function. -1, 0 across this function gives you -2 value. So my function at this point is -2, which doesn't affect any of these 2 values because root 13 larger than 2. And that's why still root 13 is a max and negative root 13 is a mean. But this line must be here, otherwise your claim for max and mean is not without a flaw. Any questions? Now, it's a beautiful method for 2 reasons. It uses shiny parameterization. It also relies only on the first year stuff. The problem with this method is it is not always that you can come up with such a beautiful shiny parameterization for the constraint. Let's just go back to my main set of slides. Look at the other two problems here. Like this problem, that's a constraint, and that's another constraint. For these two, even if you make an effort and if you parameterize these constraints, they no longer will be as good as cos and sine. There will be some sort of asymmetric, horrible equations where when you start differentiating them, it will give you even more horrible looking derivatives. That's the beauty of the Lagrange method. The beauty of the Lagrange method when you use it is this. It doesn't ruin the symmetry. If the symmetry is present in the constraint, and there's a very nice symmetry here, circular symmetry, very nice symmetry here. It's the axis symmetry along the around the bisector. If the symmetry is present, Lagrange method will keep the symmetry, and that probably will help you to find the problems easier. Yeah, that's right. So let's just discuss with you what the Lagrange method is about. Oh, sorry, yes.
I think that last example was wrong. It should have been -2, f minus 2, 0 instead of f minus 1, 0, because it was 2 cos t instead of cos t. That's a game. That's right. Thank you very much. That should be -2, which makes it -4. And now actually it does change a thing, right? I should move this here. So not only it's just that the solution will be flawed, it will be a wrong solution if you overlook this little piece, isn't it? That's interesting. Thank you. Thank you for bringing this up. That's scary, isn't it? Yes?
When you talk t as an element of like negative pi to pi, do you have to include one of the ends?
You don't have to. I mean, to cover the circumference of the circle, you need only one end.
But that would change the max and min because
no, it won't.
Continuous point.
I didn't catch it. Why do you think it will change the max and min? I made it closed interval. I mean, from the point of view of the problem, you can drop one of the ends. You still will have this point. I made it closed because normally when you do min-max problem in the first year, you always do it over a closed interval. The reason for that, because continuous function always has a max and min over the closed interval, bounded closed interval. It's a max-min theorem for the compact subsets. That's why I made it closed. But in the context of the current problem, it's irrelevant. You can include it, you can drop it, one of the points, not both of them, of course. And that will work, yes?
So when you're taking t from -5 to pi, can't you also take it from 0 to 2?
You can. Yes, but then this point will be the inner point. That will be an inner point. It's a good point, actually. Well, let's just do it like that. It looks like I made a mistake somewhere. Let's just double check the computations. If I take this cos and this sine across my function, I think I did maybe. I just miscalculated somewhere. That's right. That's a good point. If you move this from 0 to 2 pi, it's bad. That point cannot be a point of stationary because derivative there is certainly non-zero. So this mean not supposed to be here, and that's an indication that I made an arithmetic mistake here or here. That's actually a good. On one hand, it's good that this happened because it's a good way to double check things. I made a mistake here and here. I'll just double check. So my function is here: 4 cos plus 6 sine. These are the values which I have to put across here. 4 times 2 is 8. 6 times 3 is 18. It's 26, isn't it? So that's right, I made a mistake here. It must be another 2. So that's right. So here's what should be 26. Should be 26. It's going to work or what? Something goes wrong today every time, right? I see what's wrong. Should be 26 here, which makes here double. Oh, double over 13, and the same alteration must be done here. That's right. So this mean goes back in the right place. Thank you very much. It's a good point. Any other objections? Arithmetic mistakes may lead to this sometimes, but this understanding of the circumference of a circle actually helped us to find place where we made a mistake. Let's just go back to the main set of slides now. Everyone is happy with this? I can close this, right? Okie dokie. So let's just see what the Lagrange method is about. So it's just like an explanation of what I just said before. You take this constraint, in this case it's a circle, as it's the first problem is discussed here, and we need to maximize the function over this circle. That's the same slide. So the whole idea which came to Lagrange is this. Let me just take the other picture, actually. Let me just take this picture. Yeah. The whole idea which came to Lagrange is this. Well, I use this the same example. So these blue lines, which are drawn across this picture, these are some level curves of my 2x plus 3y function. And, well, by the nature of my function, you probably can see after a while that these constants, which is associated with these level lines, they grow in the direction of the northeast. So it's the direction of the first quadrant. So the higher the blue line in the first quadrant, the higher the constant value associated with that level curve. So the max we found in my parametric solution, it's the max which sits here, you see? So let's take this extreme point where my level curves, they barely touching my constraint and then just depart. That's where the extreme happens. And the Lagrange suggests how we can spot this moment where my line leaving the constraint using the vector language. He says, look what happens. If you picture the gradients of the level of the constraint and the level curves, the green vectors are the gradients of the level curves. So this function, basically, they're all the same gradients. Gradients doesn't change from level curve to level curve. And the red ones, that's the gradients of the constraint. If you take these gradients, this thing which happens when you arrive at the point where you depart from the constraint, you can test this by the fact that the gradients there are parallel to each other. This was his ingenious observation that when your function leaves the constraint, the gradients, they just became parallel to each other, and that was the basis of his criterion. He said the points where the extreme is happening, it's the points where one gradient is parallel to the other gradient. And that is what I said on the theorem, which I flicked through on the previous page. Let me just go back to that page. Here it is. It says that if you have a function f and a constraint g in any dimensions, even though I made the demonstration in 2 dimensions only, the test for this point where the extremity is happening, this test, one gradient is parallel to the other gradient. That's right. And, well, it's parallel with some unknown coefficient. The method is called the method of Lagrange multipliers. This coefficient which appears there, that's the Lagrange multiplier coefficient. You can, I mean, it is often happens when you try to solve this system. Now you can, I mean, like when you write up the Lagrange equation, the next step will be solving this system, finding those points which satisfy this equation. It is often the case that you don't even need to find the actual value of Lagrange coefficient. You can use some symmetries in the equations to come up with the values of x and y straight away. And that's, you see, I said the symmetries again, that's the beauty of the Lagrange method. It doesn't ruin the symmetry of the constraint nor the function. And that's why the symmetry is present here in the equations, and that sometimes symmetry is very, I mean, it is very often you can use that symmetry to your advantage when you solve this system. Unlike when you do parameterization, when you need to ruin the symmetry most of the time, unless you have very good parameterization like circles or ellipses, something like this. So, and this is it. Basically, well, the paragraph says that this is just the candidates for the place where the extremities may happen, but it's not really a big deal because you have only a finite number of candidates. You can run through these candidates and choose the max and choose the mean. Right, so we just saw this. Let's just try to do the whole example now with the Lagrange multiplier. The same example we do now formally with the Lagrange multiplier. We use his criterion, his ingenious observation, that these points where the extremities happen, it's the points where one gradient is parallel to the other gradient. For these two functions, that ends up to be this vector equation. Gradient of my f function is a constant vector, 2, 3. Gradient of my g function, the constraint function, is the double x double y, is my Lagrange multiplier. And it is a case in this solution that actually we don't care, I mean, we don't need to find this Lagrange multiplier because look what it says. We can divide this equation first by second. Actually, the equation doesn't do that. Actually, well, if it was my solution, I would have just divided first by second. That will cancel out lambda, and it will give you this relation. Y by x is 3 by 2, which you can use together with the constraint relation and find x and y straight away. If you do that, it will be x and y. Is my cosine sine from my parametric solution. It's a lot quicker actually, right? No derivatives of cos, no derivatives of sine, no trigonometry, like it or not. It's a lot quicker solution. The reason for that, it's a symmetry. It's a beautiful method, ingeniously beautiful method. And it's ubiquitous method, as a matter of fact, in many optimization problems. And that's the end of it. So we use the first two, which came from the Lagrange condition, to find the relation between y and x, which we put across the third equation, across the constraint. That gave us the value for x and y like this. You can check the arithmetic, but it should be fine. So here's my candidate's points. It claims 4 here, and it was 2 in my case, right? Well, I think we're right here. This slide has a typo now. Hopefully, but one of the slides has a typo. I'm sure you'll figure out which one. But I insist that this one has a typo. But don't take it for 100%. Any questions? We have another 2 examples, which we can do with the Lagrange. You can try to do it with the parameterization, like this example. The other one. You can try to do it with the parameterization. You can easily come up with the parameterization for this constraint. You can just solve here for x, right? You say y equal 20, take double x by 3. Then you call your variable x t parameter. Here's your parameterization. You take this parameterization across the function, you end up with the one-dimensional problem. But it's a horrible function. It's no longer the symmetric one. It's difficult to differentiate. Whereas when you do Lagrange, the symmetries they persist through all of the considerations. If you're smart enough, you can exploit that symmetry to your advantage. So if you do Lagrange here, we do Lagrange here. The same gradients, this time we swap them around, these gradients. So that's my function this time. This is the constraint, gradients. The same gradient, just the lambda coefficient went on the other side, next to the constraint, which is actually not a big difference. Well, same equations. You take the quotient of 1 and 2, you end up with the relation for y and x, which you take across the constraint, and you find x and y at the same time. Here it is, 40 by 13, 60 by 13. I beg you to try the parameterization method, because if you try it, you would love this method. Look, 2 absolutely distinct problems. If you try them doing via parameterization, will be absolutely distinct solutions. One with cosine sine, the other one with some horrible parameterization. Via Lagrange, almost the same lines. And the point. Only one point, by the way, that's a difference from my previous solution. In the previous solution, we had 2 points, min and max. This is not an accident, I'm sorry. The reason for that is this. In the previous problem, constraint was a circle, which is bounded and closed, which is compact. And for that, we have min-max theorem. Continuous function always takes max, always takes min. And we had them through Lagrange or through parameterization, doesn't matter. In this case, constraint is not compact, it's a straight line. So nobody guarantees max or mean. This point we found, we still have to classify it into max or into mean. How do we do that? There's nothing to compare with, right? When you have 2 points, max, mean, which are guaranteed by the main-max theorem, you can compare. One is max, the other is mean. When there's 1 point, what to do? Well, here you can either exploit the nature of the problem. In this case, the nature is, you can interpret it like that. X squared plus y squared is a distance. So basically we're trying to find the extreme distances from the origin on this red line. Obviously there's a mean, the closest point to the origin, somewhere here, the base of the perpendicular, and there's no max, right? You can be as far as you wish from the origin if you go one way or the other. So that point we found, that's a point of mean. That's how we classify the point. I used the nature of the problem, the nature of this function. It's a distance function. Sometimes you can use the other way. You can classify the point by taking some other point on the constraint, any point. If the point you come up with is a mean point, no matter which you take, your point will be less. And if it's max, it will be the other way around. But in this question, it's just we use the fact that x squared plus y squared is a distance. And that's why the point we found is a mean point, not the max point. Next example. X squared plus y squared, again, distance function, and another constraint, 2 hyperbolas. Again, they are not bounded. That's why it's not a compact case. That's why we probably don't have mean and max at the same time. Mean-max theorem doesn't work. But we will have mean, again, due to the nature of the function. It's a distance function. We will have it somewhere here, or maybe here. I don't know where the closest point is. Lagrange method will tell us in a few lines. Here we do Lagrange method. 2 gradients for f function, for g function, Lagrange condition in vector form, in component form, Lagrange equations. Again, we can exploit the symmetry. We can quotient one equation by the other. Here, 1 by 2. If you quotient that, you will end up with x squared equal y squared. Which means that we lie either on bisector or on the other bisector. So if you take this condition across the constraint, across this one, actually we can rule out the possibility of minus here, right? I mean, the first 2 conditions, the first 2 Lagrange conditions, they suggested y equal plus minus x, but the constraint, as a matter of fact, rules out the minus case because if xy product equals 16, they must be of identical sign, plus plus or minus minus. That's why even though from the first 2 we have plus minus, the constraint itself rules out the minus case. So we have y equal x, we have only one bisector, and that's where my function takes the mean value. Plus plus 4 or minus minus 4. And if the value itself, well, if you take it across this one, it will be 32, isn't it? It's a minimum. It's a minimum value, and that is because we know the nature of this function. It's a distance function. Yeah. Actually, we found 2 points, but those 2 points, they both deliver minimum. Geometrically, it's clear because we have 2 branches. On both branches, we have a point where the distance is getting its minimal value. Any questions? So it's a really good method, especially when it's only one constraint. The system of equations you will come up with, they will be nice and symmetric and everything. With some experience, with some effort, you will learn how to exploit that symmetry to your advantage, and the solution will be brief and beautiful. Well, the same method works when you have function of free variables. Another example, let's just look for that. It's the function of this type, 1 on x, y, z, and we have to minimize this function across this constraint. This is the ellipse, it's the ellipsoid. This time it's ellipsoid, right? This is the equation of the ellipsoid. It is a closed and compact subset. This time we will certainly have max, we will certainly have mean. No exception. If you don't, as a result of your solution, it's the indication for the double check because you did an arithmetic mistake somewhere, like I did today, and I did a double check. So let's just see what happens. Here's a Lagrange condition in vector form, in component form. This time we will have 4 equations, 3 from here, and the constraint, all of them here, all of them here. Let's just see what happens. All right. So the idea here, again, that's the idea how to exploit the symmetry. On all of this, in this 3 first, what is done is that every extra factor moved on the right-hand side so that you end up with 1 on x, y, z all the time. So if you move this 1 extra x here, if you move this 1 extra y here, if you move this 1 extra z here, in the third one, you will end up with this long line right in here. Which suggests, because this is the same value, right? Negative 1 on x, y, z, it's always the same. It suggests that this x square, y square, and z square, I mean, in these equations, I mean, when I say these equations, I mean it's 18 lambda x squared equal to the left-hand side here, first equation, double lambda y squared equal left-hand side here, and double lambda z squared equal left-hand side here. Actually, we don't care about that, so I'm sorry, it's too my explanation right now. What I was trying to say is too complex, actually. Just look at these two. You cancel out lambda, you cancel out 2, you will end up with the 9x squared equal y squared. You look at this one, you cancel out 2, you cancel out lambda, you end up with the y squared equals z squared. You take this across the constraint, across here, and you will end up with value for z, and for x, and for y. That's one of the values. Actually, it's the only value because there's an extra assumption in the question, you see, x, y, z positive. Otherwise, if there wasn't such an assumption, then you have to consider all possible combination of signs, plus, minus, plus, minus, plus, minus. All of them will work with the constraint. All of them will work with this condition, so all of these candidates must be considered. But because of this extra assumption in the question, we don't need to do that. Just one point of interest. Right. And we end up with a value like that. How does it go around with what I said before I started this question? I said the ellipsoid is compact, it must be max and it must be mean. Did I lie to you? Or maybe the mean max theorem lied to you? The mathematics is in danger, we have to save it now. What do we do? Where's the problem in what I said? I said mean, it's a compact thing. The mean max is supposed to give 2 max and means. We have only 1. What the heck is happening?
Extra constraint.
Which constraint?
X squared 0, y squared 0.
Well, it's not a constraint. Constraint is something when you have equal sign. It's more like a domain. It's the first octant in space. But why do you think it will ruin what I said before?
It's an open set. It's not open.
It doesn't make it compact anymore. That's right. That's why I lied to you. I said ellipsoid is a compact. I said it's closed and bounded. That's an outright lie. What? No, sorry. No. The ellipsoid, of course, it is closed and bounded. It is a compact set. But when you take the part of the ellipsoid in the first octant together with this piece, that's where it stops being closed. That's where it stops being compact. And that's why mean max doesn't work anymore. If you bring back the whole ellipsoid now, without this first octant restriction, then you will have multiple points, plus, minus, plus, minus, plus, minus, and then you will have mean max. I think you can even say what the value will be, because it's plus, minus. When you take across this function, it will be either plus or minus. So the other value will be negative 9 root 3. So plus value will be max. Minus value will be mean, right? Are you with me? But now, that's right. No, actually. Well, it's a beautiful problem, actually. So many pitfalls in here. So many places you can stumble and fall. Here's another interesting thing to you. Listen to this. Listen to this. No, listen. Let's just bring this whole ellipsoid together, right? It's supposed to have max and min over this ellipsoid, right? Obviously, max will be 9 root 3, and the min will be negative 9 root 3, right? Now, back to this problem. I just cut only the 1/8 of my ellipsoid within the first octant. The rest is gone. Only one value stayed, 9 root 3. And now the slide claims it's minimum. How come? Before it was max. Before it was max across the whole ellipsoid. Now I took the only part of the ellipsoid and it became min. What happened? Science in danger again. What do we do? Where was this thing I lied to you again? Well, I lied to you in the other thing. When I said min-max theorem, there's a second condition that the function is supposed to be continuous. This function is not continuous across the whole ellipsoid. It's a division by 0, right? When you cross the planes, it will be x or y or z equals 0. You will have division by 0. The function is not continuous. That's why min-max for the ellipsoid with this function doesn't work. Even though ellipsoid is compact, the function is not continuous. So min-max still doesn't work. And that's why the slide is correct, and my statement before was another outright lie to you. Okay? Now, how did they conclude that this is a min now? Before, when we had such a case, when min-max didn't work, we used the nature of x squared plus y squared. What happens this time? Well, this time we can use this informal argument. When you make a point on the ellipsoid very close to one of the planes, then the denominator will go infinitely small, right? I mean, your x or y or z will be closing to 0, which means that the reciprocal will go to the infinity. And that's why your function will have infinitely large values on your ellipsoid. This function, 1 on x, y, z. And that's why this must be minimum. That's the argument which explains why it is minimum. Okay, any questions? Right. Well, now I have to just briefly tell you what happens when you have not one but more than one constraint. In this case, well, the whole idea works in a similar way, and that's just right here. So this time, when you have not one but many constraints, 2, 3, 4, or even more than that, Lagrange principle work in a similar fashion. It says that the points where extremities will happen, it's the points where gradient of your function is a linear combination of the gradients of the constraints. In case you have one constraint, it was parallel, right? It just was only one gradient. In case more than one, you have this linear combination. You'll have more multipliers, so the system you need to solve will look not as simple as when you have only one constraint, but still it will have some symmetries, and with some effort you can, sometimes it can be solvable. In the questions you will have in this topic, there will be some symmetries, and you will be able to exploit that. Sometimes even with Lagrange multipliers, sometimes it may be quite hard systems, but you won't see the systems in this topic, so don't worry about that. Just keep in mind this general principle that when you have more than one constraint, you have to replace this parallel condition with a linear combination condition with more multipliers, like it is on here. Yeah. Well, here's the example. That's a typical example you will see. It's a relatively easy example. We have to minimize or maximize this function, which is, thanks God, continuous, no more lies, right? Over two constraints. This is a cylinder, right? In three-dimensional space, it's a cylinder, radius 2, stretched across the z-axis. And this is a plane which cuts through the cylinder. If you cut a plane if you cut a cylinder with a plane, in a cut you will have a circumference of the ellipse, strangely positioned in space, right? So you have this little curve, thin curve in three-dimensional space, which is a cut of the ellipse of the cylinder by some inclined plane, and we need to minimize and maximize my function across this ellipse. Well, this time min-max works, and this time you can trust this, hopefully. because function is continuous. Ellipse is a bounded closed set, so it is compact. We will have mean, we will have max, and doing this by parameterization, it's a nightmare. Trying to find this parameterization for this ellipse, you can find this, of course. You can take cos and sine here for x and y, and then you can solve for z from here. That will be your parameterization. X will be root 2 cos t, y will be root 2 sine t, z will be 1 take root 2 cos t. That's the parameterization. You can take this parameterization across this function and you can solve one-dimensional problem, first year problem. You can. It's a lengthy and unpleasant solution. Lagrange multiplier offers you another solution. Look at this. Here's a Lagrange condition with two multipliers, all of them expanded here. Left-hand side, that's the gradient of f function, which is easy, 1, 1, 1, linear functions. Right-hand side, gradients of my g1 and g2, right here. Let's just see what the slide says. The third one straight away says to us that the second multiplier must be 1. The first one from this line cannot be 0. That's why they conclude that lambda 1 is not 0, because the product equal 1. Neither of the factors can be 0. So you take lambda 1 across here, which cancels this one. So you have 2 lambda 1 x, and lambda 1 is not 0 from the second equation, so x is 0, which is here. When x is 0, you can solve for the rest from the fourth and fifth equation, and that is what is done here. That's the strategy which is used here. Every time you have to come up with some ad hoc strategy, yes, you have to do it. But it will be easier than if you parameterize this piece. Like again, I said, I beg you to try it to believe in the Lagrange method. And so we have 2 points, 2 possible points where max and mean happens, and we must have max, we must have mean. That's the mean-max theorem. And here they are, 1 plus root 2, 1 take root 2. Any questions? Okay. Well, there are 3 pages left here. There are other examples on those pages. I don't want to discuss them, as a matter of fact, today. I think what we discussed so far is enough information for you to absorb, and then you can just get through those examples without my help. I was planning to discuss with you some other example, which I call Holder inequality. That's the inequality which can be proved again with the help of the Lagrange multiplier. The reason I chose that because it has some bearings on our earlier discussion of metrics. If you remember that, we discussed metrics with you on week 1. I have 6 minutes. Well, why not? I'll try. I mean, at least first example here. So look at this. So that is where the Holder inequality, the inequality itself is here. That's the inequality. If you take a combination ax plus by, all of the things here are non-negative. Then you can control it by this strange product, like so. You know what? I'll do it differently now. Instead of showing the proof for this Lagrange, for this Holder inequality, I included this as a part of the tutorial set. When it comes to Lagrange multipliers, there will be such a problem. And I will publish the slide with a solution. So you will attempt that problem. I mean, those of you who like challenges will attempt that problem. If you have any difficulties, you can go back and look at the slide, which I will publish. But what I'm going to do in the remaining 5 minutes, I'll show you the connection of this inequality, if you believe in it, and after you prove it, you will believe in it, with the metrics we discussed with you on week 1. So I need to switch to the other slide. So just take a mental picture of this inequality. I will switch to the other slide. Oh, no. If you believe in this inequality, like I said, it will be in the tutorial sets, and I will publish the solution in case you won't be able to reconstruct it on your own with your tutor or any other way. if you took a mental picture of that inequality, which had ax, by on the left-hand side, you will understand this left-hand side. So you see, I replaced a and b with a1, a2, a3, an. I replaced x1 and x2, sorry, x and y with the b1, b2, bn. So it's the same expression, but this time we have n terms rather than 2 terms. And I replaced a and b with a indexed and x and y with the b indexed. Right-hand side, here it is. That's how the version of the right-hand side of that inequality will be if you use a's instead of x and b's instead of, I'm sorry, a indexed instead of a and b indexed instead of x and y. And I also changed the p and q into alpha and beta. That's the relation between alpha and beta. Here's a little alpha, here's a little beta. So that Hölder inequality which I showed you on the other slide, that's the one which you're going to prove. This is a slight development of that inequality, just I throw in extra terms, let's just throw in extra terms. Why did I do that? Because before I do that, this is the same inequality but with the sigma notation, you see? The sigma notation for the left-hand side, the sigma notation for the right-hand side. It looks a lot better in sigma notations, as a matter of fact, shorter and more structured. Now, why did I do that? We discussed with you matrix equivalence. Remember, on week 1, lecture 3, it was on the Moodle. You can see that there was a result there, like this, which I told you it's hard to prove. There was a theorem there with 3 parts. The first 2 we proved with you. The third one I said difficult to prove. Well, now we can. So there was a relation between p and q like so. The matrix, that is what the matrix is. P metric is something like this. So the left-hand side, we proved it. It was part of the first 2 parts of the theorem. This one I said is a hard one because this is a new 1 on R appears. Can I just zoom in a little bit? Yeah. This is a new 1 on R here appears, and the relation between 1 on R and 1 on P and 1 on Q is like so. So if you believe in this Hölder inequality, which you can prove with the Lagrange multiplier method, we can, I'll show you the proof, you'll try it on your own. This right-hand side, it will come up nicely with the help of the Hölder inequality. Look at this. I take the middle metric, so my x vector, it's the one which composed of these components. My y vector is like so. So look what's going to happen. I'll keep it like this. That's my Hölder. I'm going to use it in a few moments. So here's the sum, or just so far I didn't take any root. This is a sum which represents this Q metric. Root, I just put it aside for now. If you just represent the sum like this is a case for the Hölder. This will be A, this will be B. If you call this factor AK, if you call this factor 1 BK, this is a case where you can use Hölder, left-hand side. If I now use Hölder, and look what I'm going to choose for alpha and for beta. If I choose this value for alpha and this value for beta, they are subject to this constraint, or this condition. You can easily check that. Look at this. This alpha and this beta, if you compute, well, I need to move it like this a little. Because this relation gives you equivalent to this relation, right? If you take this q across the enumerators here, it will be 1 on alpha plus 1 on beta, and it will be 1. So that's how you apply the Hölder to the left-hand side here. I introduce this trivial factor 1, that will be my b, this is my ak, and that's the choice for alpha and for beta. If you just use directly Hölder with this choice of alpha and beta, that's what we're going to come up with. This is the first factor in the Hölder inequality, my choice for ak, my choice for alpha, my choice for alpha. If you take this choice next to the q power, it will be p power. Here's my choice for b, and here's my choice for beta. And we're done. Now if you take this, remember the Q metric, it also has root. If you apply root around here, it will kill this Q enumerator, it will kill this Q enumerator, and this sum is n. This is this factor. This is this n factor. Do I have it here? No, I don't have it here, but that's the end of it. So this mysterious relation, which I left open back then, I didn't expect actually that I'm going to prove it, but now I realize I can, with the help of Holder and Lagrange Multiplier method. Now you can see how this 1 and R appeared. Well, there's still a little missing bit, the Holder itself, but it will be a part of the tutorials. I'll publish the solutions. There will be a hint in the question itself, so you will be very well equipped to take that challenge and successfully manage that challenge. I hope you will. Any questions? If not, thank you very much. We're done today.